Do you remember your definitions? So if I asked for the heat of formation, what has to be on the right-hand side? 1 mole of the substance and nothing else. So if I ask you for the heat of formation of methane, then all I have on the right-hand side of the equation is methane. What is on the left-hand side for, let's say, heat of formation for methane? Okay, April, I'm not quite sure if that was in response to the previous question. So I do have a 1 mole of methane on the right-hand side, but I don't necessarily need to have 1 mole of anything on the left-hand side. What I do need to have is, great Caleb, I need to have the elements that make up methane on the left-hand side, and they have to be in the standard state. So, correct Caleb, methane is made out of carbon and hydrogen, and you have to state the allotrope of carbon, and in this case it's graphite. The standard state for carbon is graphite. Okay, so heat of formation, it's always a 1 mole. So heat of formation of sulfur dioxide, I only have sulfur dioxide on the right hand side, and I only have elements on the left hand side, and the elements have to be in their standard state. Okay, the next one is the heat of reaction, and this is the one that applies to anything sort of thing. It's just simply the reaction as given. So it can be 2 here, it can be 4 here, it doesn't matter. The heat that's released or taken up has always got to apply to the reaction as given. So if I had a 4 here in front of the NH3, I would have twice as much heat released or taken up. Or if I had only 1 over here, I would have only half as much heat released or taken up. Does that make sense? So the heat of reaction is just simply for the reaction as given. Okay, the next one is the heat of combustion. So the rule for the heat of combustion is I'm reacting it with oxygen, and it has to be for 1 mole of substance we're burning. So here the substance has to be now on the left-hand side. Remember up there it was for the right-hand side for formation. Here for combustion, the substance we're dealing with has to be on the left-hand side together with oxygen. And there has to always be 1 in front of that substance. So if I was burning methane, it would be 1 CH4 on the left-hand side. I mean, obviously in chemistry we don't write 1s, but okay. And because we have to have a 1 there, we can get fractions. And then what goes on the right-hand side are the common oxide of whatever is being burnt. So if this was a combustion reaction for sulfur, so it's sulfur on the left-hand side, or 1 of them reacting with oxygen, this is the common oxide. You couldn't make sulfur trioxide because that isn't the common one. Sulfur dioxide is the common one. Okay, and anything with carbon and hydrogen would have carbon dioxide and water as the products. So I see April is typing, so I'll answer that when that's done. Okay, so you add O2 to the substance. Yes, you're pretty much burning it in O2, and you're forming always the common oxide. So if it was carbon, you're forming carbon dioxide and not carbon monoxide. If you wanted to do carbon monoxide, then you have to do a different reaction. You can't use the heat of combustion. You'll have to use a general heat of reaction and work it out, and we'll show that with Hess's law. Then the heat of fusion and the heat of vaporization and also the heat of sublimation. These are just the change of state ones. So it's always 1 mole of the substance going to 1 mole of that same substance in the different state. So fusion is solid to liquid. Vaporization is liquid to gas, and sublimation would be solid to gas. And if you wanted to go the other way around, you'd have to reverse the reaction and change the sign. Okay, so are you quite clear on those definitions? Because you will have to write equations based on the definition. Yeah, okay, we'll have lots of practice. Okay, so here's, and I've had this one up here, which I'll show just now. When you use the heat of reaction, for instance, what you've got is a difference between the products and the reactants, that energy that's given off or taken up. In this case, it's an endothermic or exothermic reaction. So if I'm going from energy of products down here to up there, endothermic, just as a revision. And April, I see that you've got to memorize them. That's fine, it's you'll get there. Okay, so that energy will be the same regardless of which way I get from those reactants to those products, whether I do it in a single step or whether I do it in 10 steps. I'm going from energy of reactants down here to my energy of those products up there. Okay, and that's what we're going to be using in Hess's law. So we can say the energy that's been given off is I subtract the energy of my reactants from the energy of my products, and that will be the energy that's, well, I've said given off, but it could also be taken up. So Hess's law is based on that, that I can work out what my heat of reaction is by just looking at the energy of the products and the energy of reactants, and whether I do it in 1 step or 10 steps, it has to be the same. So let's have a look at it. Hess's law, if you want to spell it out, it states that the enthalpy in a chemical reaction is independent of the pathway. That's just a fancy way of saying I can do it in 1 step or 10 steps, it makes no difference. So it doesn't matter which way we get there. If I start from A and I land up at Z, whether I go A to Z or A to B to C to D to E to Z, it's that difference in energy is going to be the same. Does that make sense? Yeah. So I'm just going from this energy to that energy. And it doesn't matter if I go up and then down and up and then down, it's still that difference in energy. So here we've got an example of, remember what I said about if I was going to say burn carbon, the heat of combustion is always to carbon dioxide. And what would happen if I wanted to do to carbon monoxide? What would then that amount of energy be? So we can play around with equations until we get to the equation we want. So as an example, if I burnt methane, okay, the heat of combustion with methane, so I do say a bomb calorimeter. Remember last time we were talking about how we actually get these values by using a calorimeter where we burn the methane, and that burns in oxygen. And remember, the heat of combustion is always to the usual oxide and water. So I can measure practically in a bomb calorimeter that I'm going to have 890 kilojoules per mole being released. That's what the negative means. Okay. If I burnt, if I wanted to say no, what would happen if I used methane and got to just the CO stage? I could work that out by, say, burning carbon monoxide to get to the same state. So can you see I'm trying to work out this bit? So if I know that, and I know, so delta H1, and I know delta H3, because I've burnt carbon monoxide, to carbon dioxide, can you see I can work out this step in the middle? Yep, so it's by subtracting them. So this is like the shorthand version, sort of going in like one step, but you can do it in multiple steps and you'll get to the same place. So I just want to get out of here and show how we can work this out with this interactive. So I think this should also be on the OTL site. Can you see at the moment I've got no reactions in here, so my final reaction is 0. Is this clear enough to see? Yep, okay. So if I drag this down, doesn't matter which way I do it, okay, I've only got one reaction that I'm adding up at the moment, so can you see it's being just simply repeated down here. So if I've got delta RH of plus 4.2, it's still plus 4.2. Okay. If I'm adding another reaction, because this is really what Hess's law is, we're just combining reactions and subtracting reactions and getting to the reaction we want. If I use this one as well, this one releases energy. Now, when I add them up, I've got SnCl2 and another tin chloride. So if I add them up, can you see I've got 2 tin chlorides? I've got titanium bromide and chlorine. So there's my titanium bromide and my chlorine gas. Now it's always a good tip to have your arrows below each other. So this way you'll know always what's on the left-hand side of the equation and what's on the right-hand side of the equation. So when you're doing Hess's law, draw your arrows in the middle of the page and then have all the reactants on the left-hand side and all the products on the right. It just makes it easier to see. And then can you see, if I add all this up, there's my tin bromide, here's my tin chloride, and here's my tin tetrachloride. The titanium chloride and my tin tetrachloride. So can you see, if I add these up, positive 4 minus 195, I'm going to have minus 190.8. Yep, okay, and because I'm just adding or subtracting, depending on which way you view it, the significant figures is not important. You don't round off to 3 significant figures. You just keep to, whatever is given over there. Okay? Right, if I reversed this equation, look at what happens. So you've got tin chloride on this side, or tin dichloride on this side, and tin tetrachloride on the products, and I've got a negative reaction. If I change this around, now the tin tetrachloride's on the left-hand side, and my chlorine and tin dichloride's on the right. And can you see what's happened to the sign? What have I done to it? I've reversed it. So whenever you reverse a reaction, you reverse the sign, because you're changing it from an endothermic to exothermic or an exothermic to endothermic. Okay, now if we look at what the final equation we've got, do you notice my tin chloride, I've got tin chloride there, I've got tin chloride here. Do I have tin chloride, and I don't mean the tetrachloride, but do I have the tin dichloride in the bottom in my final reaction? No, because this is what we can use with Hess's law. I can cancel this one. I've got 1 tin chloride on the left-hand side of the reaction and 1 tin chloride on the right. And look, they're both solids. That's the other thing you've got to check. You can't just cancel any old one. You've got to make sure they're in the same state. So that tin chloride in the solid state cancels out that tin chloride in the solid state. So I've got no tin chloride or tin dichloride in my final reaction. Okay, that's the only one that's cancelled out. All the other ones are still there. Yes, I mean, here I'm just playing around and showing what's happened, but that would be why when you're trying to get to the equation you want, you may have to reverse the reaction, you may have to double the reaction or halve the reaction, just to make sure things cancel the way you want it to. So I could take this last one down now and bring it down here, and notice what's happened. Okay, it's an exothermic reaction. I haven't swapped it around, but can you see what? Yep, so April, do they cancel on either side of the arrow if they are the same amount? Yes. So if I've got 1 on the left-hand side and 1 on the right in the same state, they'll cancel. If I've got 1 on the left-hand side and 2 on the right-hand side, the left one will disappear, and the right one goes 2 subtract 1, it goes down to 1. So you will still have something on the right hand side, but only one of them, because I had 2 originally and it goes down to 1. So there must be the same number and the same state. If I had liquid on one side and solid on the other, they will not cancel. Okay, so I've taken this one down as written. It's minus 273. I haven't reversed it, so it's still minus 273. But notice now when I add these 3 reactions up, it's going to be different again. Now Joe said, what about aqueous? Again, it's got to be aqueous on the left and aqueous on the right for them to be able to cancel. So you can have a heat reaction with aqueous, but if you want to cancel them, they must be in the same state. Okay, so can you see here what I've got? My tin dichlorides have cancelled, and sorry, titanium, not tin. Titanium dichloride, TiCl2, has cancelled with that one. And what else has cancelled? My SnCl2 has cancelled with that one. So all I've got left is the tin bromide and the tin tetrachloride. Oh, because the chlorine over here has cancelled with the chlorine over there. So this is the way you would use Hess's law, is you would just swap them around until you get to what you want. So let's go and do some examples. And I'm going to teach you a short way and a long way and tell you when you should do which one. So let me just go from current slide. Okay, right. Sorry, that went sort of from the beginning. Okay, so this is now the short method. So I want to go from those products to the reactants. You use this method when you are given everything as heats of formation, because then I know the exact energy of the reactants and I know the exact energy of the products. Okay, so notice, use the delta FH values, and I've just given you heats of formation. If I start muddling this up with reactions and so on, it probably will not work. So you need to work out the energy, the delta H for this one. So you're trying to work out the delta RH for this one as written, given all these heats of formations. So what you basically do is you say, okay, I've got thionyl chloride, that's SO2Cl2. Sorry, that's not thionyl chloride, that's SOCl2. Anyway, you've got SOCl2 as a reactant. You've got, and that's that one over there, you've got water as a reactant. So if I add those two up, that's going to be my energy of the reactants. Then the same thing with HCl is my product, and there it is in the table, and the same thing with the sulfuric acid. Okay, so we've identified what is my reactants, and we've identified the products. So if we do this equation now, for this formula, we put in the values given here for products. So the purple ones would go here, and the yellow ones would go here. There is, though, one step I haven't said. and that is you've got to look at the numbers in front of the substances. Okay, that's 1. So if I form 1 SO2Cl2, I get given that amount of energy. So that's fine. This one though, I need 2 waters. This only gives me the energy to make how many waters? 1 or 2? 1. So I'm going to, because I need 2 of them, I'm going to have to double it. So there's my product, the products in purple, reactants in yellow. So can you see where this 2 comes from? It's because I need 2 HCl, so I have to double the minus 92. And the same thing over here, I've got a 2 in front of this value because I've got a 2 in front of the water. So that's why I need to double the minus 286. So what we're pretty much doing is you just take these values as given and you just subtract them. So just be very careful. Remember, a negative times a negative is a positive, so make sure you don't make careless errors in your equations. So okay, that was just about the 2's, making sure you check that. And so can you see I've done it fairly step by step by step, and I suggest you do that so you don't make silly errors in the beginning. But if you're pushed for time on the exam, hopefully by then you've practiced enough and will be less likely to make a mistake. Okay, do you think you could do a short? This is now, I've done the short method, this is now the long method doing exactly the same thing. Okay, so let's just go through the steps though. The equations must be balanced. If you've got unbalanced equations, it's not going to work because they're not going to cancel properly. When you reverse the sign of an equation, if you reverse an equation, change products to reactants, reverse the sign, and remember you've got to, if you multiply by a factor, say I needed 2 H2Os, I've got to double the value of the delta H, as we did in the short method. And then, as I said before, keep the arrows directly below each other. You're going to make less mistakes when you cancel out. Okay, and then as I say, check your calculations. It's so easy to forget a negative when you're doing this and you land up with the wrong answer. And then of course for excellence you need the unit of kilojoules per mole, and it's always kilojoules per mole for these. Okay, oh sorry, I thought I'd done the previous one again using the long method, but here's a different one. So I've given you just simply heats of reaction. So these are heats of reaction, not heats of formation. And I want to get the heat of reaction for this first reaction of 2NO reacting with oxygen to form NO2. So it's not quite the heat of combustion of NO, because remember heat of combustion is 1 NO and I've got 2 of them. So I just want for this particular heat of reaction. And the only information I'm given is nitrogen, the heat of combustion of nitrogen, and I'm also given the heat of formation of NO2. Can you see why this is a heat of combustion for nitrogen gas? N2 plus O2 goes to 2NO. Okay, remember a heat of combustion is one thing of that substance reacting with oxygen. Actually, it's not, sorry, it's my mistake. The common oxide is NO2, so this would not work, okay, because remember it has to go to the common oxide. So this is not the heat of combustion of nitrogen. Forget I said that. But it's good to think about it this anyway. But this is so neither is combustion. Okay, so neither is combustion. No, this one is not combustion either, because although it's forming NO2, I haven't got a 1 in front of the nitrogen gas. I've got a half. So it's not the equation for a heat of combustion of nitrogen either. Right, great. But this one is the heat of combustion for the, sorry, this one is the heat of formation of NO2, because I've got one NO2 on the right hand side and I've got the elements on the left hand side in their standard states. Okay, but as I say, if you don't know what these are, a heat of formation and a heat of combustion and whatever, they're always delta RH anyway. So why the half, Joe? The half is to balance the reaction. If this was, as I say, the heat of formation of NO2, I have to have a 1 in front of the NO2. I can't make it a 2 or anything like that. So if there has to be a 1 here, I can only have 1 N on the left-hand side. And the only way I can get 1 N on the left-hand side is to put a half in front. So is this for the reverse reaction? Well, this is just the ones that are given. So, and the way this one is given, I'm just sort of pointing out that this is could also be used as a heat of formation of NO2. Okay, we may have to reverse reactions now to get to this one. So let's start. If I want to get to that one, I need NO on the left-hand side and NO2 on the right-hand side. So with this first equation, what do I do with it? Remembering I need NO on the left-hand side and NO2 on the right. I have to reverse it. Correct. Okay, so there we go. There's NO2 that has to be there, and looking at the sign of what we need to do, and I need NO. So there's the NO, and that's fine. I've got 2 there and I've got 2 there, but I have to reverse this one. And the O2 is all in the right place. So if I deal with that one first, can you see I've reversed it? And can you see I'm keeping all my equal sign below each other? So I've got the NO left-hand side, and it's 2 NO, N2 on the right and O2 on the right. And can you see I've changed the sign? It's now minus, there it was positive. Okay, next one, if I look at that one, I want to keep the NO2 on the right hand side, so I don't reverse it. So it's over there. But notice I need two NO2s, and I've only got 1. So can you see I'm multiplying through by 2. The whole equation I multiply by 2. And I double the values. So if it's 33 for delta H, it now becomes 66. Okay, and now I cancel that N2 cancels with that N2, because 2 times a half is 1. Okay, I've got 2 O2s on the left hand side, I've got 1 O2 on the right, and so everything on the right of O2 will cancel out with 1 on the left, and I'll be left with 1 O2. And so basically I've now got 2 NO on the left hand side, 1 O2 on the left hand side, and 2 NO2 on the right hand side. And I simply add all this up to get the final answer. Minus 183 plus 66. So there's minus 183 plus 66 gives me minus 117 kilojoules per mole. Okay, so do you think this, as long as you did stepwise, you'd be able to do it? Okay, so let's look at some more examples. So here I'm given a reaction of hexane being burnt, a combustion reaction, and I need to find out the formation of hexane if I'm given the formation of carbon dioxide and the formation of water. So I'm given 3 different bits of information, and I need to get the formation of hexane. So what sort of equation am I aiming for? Formation of hexane, 1 mole of hexane on the right hand side, elements on the left hand side. So I need graphite on the left and I need hydrogen on the left. Okay, with me so far? Okay, so that's your final equation. That's what you want to add up to. So now we just look at, okay, I need obviously hexane on the right hand side, so I'm going to need hexane up here on the right hand side too. Okay, the other thing is it helps to spell out these equations as well, so we know where hydrogens and oxygens and carbons and oxygens are. So if you write, there's a heat formation of carbon dioxide and the heat formation for water. So if you've written those down, it's now easy to manipulate. What do you swap around, reverse, what do you multiply? So have a look at that. Can you see what I need to do to those three reactions? So if that's reaction 1, this reaction 2, and this is reaction 3. What do I need to do to reaction 1 to help me get this one? Well, the first one is balanced. The reaction 1 is balanced, what should be. 6 carbons, 14 hydrogens. Yep. So, well, I don't need to multiply it, April, because reaction 1 is the only one that has hexane in it. And remember, I need hexane on the right-hand side for my final equation. So the only place where I can find hexane is in that first reaction. But the issue with the first reaction is the hexane is on which side, the left-hand side or the right-hand side? The left. So how do I get the hexane that's on the left to the right? You need to reverse it. Yep, correct. So the first one you reverse, okay. What do you do with the others? So here, remember, I'm going to need carbon, graphite on the left, okay, and I need 6 of them. Okay, so the only place I can get graphite is from equation 2. So what do I need to do to equation 2? Multiply by 6. So I've got to have a 6 in front of the carbon, a 6 in front of the oxygen, and a 6 in front of the carbon dioxide. And then finally, I also need hydrogen gas. Okay, the only place I can find hydrogen gas is equation 3. But I've only got one there. It's on the right side, it's on the, not right side, it's on the correct side, the left-hand side, and this is also on the left-hand side. But I'm going to need to multiply by 7 in this case. So I'm going to have a 7 times a half, so that's going to be 3.5. 7 times 1, so that'll be 7. And 7 times 1 will be 7. So, okay, let's go for it. If I do that one first, I've multiplied through by 6. So remember, the value also gets multiplied by 6. With the second one, third one really, I've had to multiply through by 7, so I multiply the value through by 7. Okay, and the very top one, I have to reverse it. So can you see that minus there is reversing that sign, so a negative times a negative will be a positive. Okay, now we check to see that everything is going to cancel correctly. I've got 6 CO2s and 6 CO2s on the right, and on the left they're going to cancel. I've got 7 waters and 7 waters, they're going to cancel. I've got 9.5 oxygens on this side, 6 oxygens on the left hand side, and 3.5 there. 6 plus 3.5 equals 9.5. So can you see all my oxygens on the left hand side cancels the oxygen on the right hand side? And finally I'm left with 6 graphites and 7 hydrogens and 1 hexane. And then I just have to work out by adding up these things. So negative 2358 plus negative 2002 plus positive 4163, and it'll give me the final answer. Okay, I see Caleb is typing. So I just want to carry on though, and then I'll come back if necessary. So here's the same one using a short method. Sorry, Caleb, if you were referring to the previous slide, I don't mind going back. Okay, right. So here we can use this short method as well because we are given heats of formation, and that's then easy to do. So if I wanted to find out the formation for hexane, because that's formation and that's formation and that's formation, I can say, right, then this reaction, you know, you've got to flip it around a bit more, is really the formation for the CO2 and water. So I'm doing it now for this reaction. Okay, so CO2 is over there, and I'm going to need 6 of them. 7 for there. This is the one I need to find out, so call it X. Okay, and that's oxygen. Now, if you think of the heat of formation for oxygen gas, if you wrote the equation down, how would you write it? I've got to have oxygen gas on the right hand side, one of them, so it'll be O2 gas. And on the left hand side, it's got to be the element in its standard state. So I've got O2 gas going to O2 gas. Is there any change? No. So any heat of formation of an element in its standard state is going to be 0. So this value is always going to be 0. So if I had, this is only for elements, so if I had the heat of formation of copper, the heat of formation of nitrogen gas, the heat of formation of chlorine gas, the heat of formation of white phosphorus or something like that, well, no, red phosphorus, because that's the standard state one, those will always be 0. Okay, so I know delta RH because I've been given it. I know all these because I've been given it. I know the element is always 0, so I can work out the one in green, which is what's calculated. Okay, so there I've substituted, and now I just do algebra, you know, put things on the right side of the equations. So I just want this on the right hand side, or just on one side of the equation, and take everything across to the other side, and I'm going to land up with exactly the same answer. So you can use the long method or the short method, but as I say, you can only use the short method here because you were given things in as heats of combustion. I had to calculate the heats of combustion. There was, not combustion, sorry, formation. Heat of formation, heat of formation, heat of formation. So if you've got all heats of formations, you can use the short method. Okay, so here's another one. So calculate the enthalpy of this reaction. This is to make ethine, and I've given you these reactions. Now, are these all heats of formation? In other words, I've got one substance on the right hand side and only elements on the left hand side. Correct, they're not. The only one that's, well, there's 2 that are heats of formation. There's this one, and there's, oh, sorry, I've clicked, and the water. But that's not a heat of formation. So I strongly, although it's written as delta RH, we know these are heats of formation. But because this one isn't, I would do the long method. Okay, so starting with that, and we're starting with this because I've got graphite on the left, and I need graphite on the left. What is the difference, though, between this graphite and that one up there, in terms of in the equation? I have to multiply it by 2. So there you go, multiply everything by 2. Don't just multiply graphite by 2 and not oxygen and not carbon dioxide. Everything has to be multiplied by 2, including the value. Okay, correct, April and Caleb, both of you. Right, there's the next one. I need hydrogen on the left-hand side, and there it is. And do I multiply that by any factor? No, because I need only one hydrogen. I've only got one hydrogen there, and I'm just given it to you, given as one hydrogen. And then the final equation is this one. Do I need to do anything with this first equation of the given ones? Do I need to multiply it by a factor or reverse it or what? Reverse, because I've got ethyne on the right and here the ethyne is on the left. So that one I have to reverse, and because I've reversed it, I have to reverse the sign. It was negative, now negative times a negative is a positive. So I do the same thing. Notice, by the way, I'm going to keep on emphasizing this, keep the arrows below each other. The two carbon dioxides cancel out, the water cancels out, the oxygen, I've got 2.5 on the right hand side here, and I've got 2 there and half there, so 2.5 and 2.5, they all cancel, and it leaves me with graphite and hydrogen and ethyne, and there's my final answer. Okay, so I must admit I enjoy Hess's Law problems because to me they're nice and logical, and as long as you go through it carefully, you don't have a problem. Okay, here's one from last year's exam. Okay, so you get given a combustion reaction and you've got to calculate the data for it given all this, and they're all formations. So could you use the long method or the short method? The short method. And that's probably the best method to go because it's the quickest sort of thing. So you just go react and subtract products. And remember, the trick here is, don't just write these down. You've got to multiply by a factor. So if I've got 7.5, okay, 7.5 times 0 is 0. Okay. But here you've got to have 6 waters and 5 carbon dioxides. But that's pretty straightforward. Okay. Any questions on that short method? No. Okay. Here is, and that was actually, I think it was just an achieve level question actually in the exam. This is now a merit level question because you can't, oh yeah, here is one where they were very, very sneaky, okay? They said calculate the delta FH for B2H6, and you get given all this boron oxide and water and so on and so forth. And then they say the melting point of boron is 2,300 degrees centigrade. Is that final bit of information relevant? Do you need it? No. That's just to throw you out and just to be mean, okay? And I think that's why that was up to a merit level question. Like, did you realize that this was not important and you did not need it for this equation, this calculation at all? You don't use boiling points for this. So again, you work out the formation. So you've got to look at what you're aiming for. So remember to form this one of that substance with elements in their standard states. Hydrogen, you should know, is H2 as a gas. Boron, hopefully you'll know, is a solid, a metalloid solid, sort of like a shiny gray type material. And you just have to balance the equation. If I've got 2 there, I need 2 there. I have 6 hydrogens on the right hand side, but because this is H2, I have a 3 in front. So where it gets tricky is if you have to start making sure you've got balanced equations. So always check that you've balanced your equations when you're using the long method. And now you just go for it. So what do you want over here? Can you see I've got B2H6 on the right hand side and B2H6 on the right hand side. So what I've done is I've taken this equation and swapped it. Okay, that one I didn't have to swap, did I? No, I didn't. This is to get the B2O3. Remember, one substance for the formation from its elements in the standard states. So boron and oxygen. And the same thing here, this would be water for heat of formation. So I'm going to have water from being made from hydrogen and oxygen gas. And because I want water, blah, 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 blah. What's my final one? I don't want any water around, so again, I'm not going to reverse the reaction because I've got 3 waters there and I want to get rid of the waters. So can you see I've multiplied this by 3? So I haven't reversed this equation. I've left it as is, but what I have done is I have multiplied by 3. So is that clear why I did this step, or what I did? Yep, so these are multiplied by 3, so that's my value. So the oxygens cancel out, 3 on the right hand side, 1.5 and 1.5 is 3. The waters cancel out, the boron oxides cancel out. So I'm left with the equation I want. Okay, always double check, and you just add it up and you get your value. Okay, right. Actually, well, let me just sort of go back. Are there any questions about Hess's law? Okay, it's pretty much guaranteed you're going to get it in the exam. I think it's been in the exam every year, so make sure you know how to do this one. Calorimetry doesn't necessarily always come up, but Hess's law has always come up in either the short version or the long version. April, do they use elements up to krypton or further? For this 91390 standard, basically you would go up to krypton. Actually, no, that's not true, because they can use xenon and so on for the Lewis structures. Oh, for the standard states. No, they won't give you any difficult ones. I mean, they may give you gold and those ones that expect you to know, but they wouldn't ask you, say, osmium or anything like that. But pretty much you know that all the metals are solid except for mercury. And then you should hopefully know by now the diatomic gases, nitrogen, oxygen, fluorine, chlorine, bromine. Well, those bromine's not a gas, but it's diatomic, and iodine's also diatomic. And then all the others are sulfur. Sorry, all the others are solid, like sulfur and phosphorus. So bromine is a liquid, and iodine is a solid. So if you sort of learn the gases and learn the 2 liquids, then everything else is a solid. Okay, right. So this is what you get if you go onto the NZQA site, and this is sort of what they tell you about the exam. So this is not important as far as you are concerned. This is just there for the teacher. So you don't have to know about resonance, you don't have to know about Hund's rule, you don't have to know about the half-filled sub-levels. Now I know in the 304.1 teacher marked assignment, I've asked you about the half-filled sub-levels. You don't have to know it for the exam. So I've still got to change that question. Okay, and you will always be given the specific heat capacity for water. And if you were given for something else, if you weren't given, it'll always be based on water, okay? Or a solution of water, and they'll tell you that specific heat capacity of whatever that solution is that, okay? Right, and then they basically sort of tell you that the periodic table will be given, which has the atomic numbers, symbols, and molar masses. So that will all be given. So you can always work out molar masses or anything like that. So it says here, candidates will be expected to use the molar masses given on the periodic table to calculate any molar masses of substances. So this is particularly important for calorimetry or those sort of things, because if you work out, I burnt 10 grams of methane, when you're trying to calculate per mole, you have to say work out how many moles are in 10 grams of methane. Okay, and then please note this. All working must be shown in calculations. You're not going to do very well if you don't show your workings. Because A, you're more likely going to make mistakes, and B, for excellence, they do want to see that working. So it's, achieved people are going to lose out by making a stupid mistake if they don't show their working, and excellent students, even if you can look at the question and get the answer in your head, show your working because you're supposed to do it. Joe, at the end of this, I'll just talk here. I'll just get back to and just find out what because I know we're down a few teachers, and I know Alison is also. Anyway, I'll go to at the end of this lesson. So after 3, I'll tell you that. Okay, Caleb, American spelling of sulfur. Sorry, that's just the way NZQA has done it. They have just simply told us they're going to use sulfur with an F, but we're going to be talking about aluminium like the British instead of aluminum. Don't ask me why. So we just use whatever the NZQA come up with, so you'll be familiar with what's given in the exam. Okay, and then, as I say, for excellence, it's important that you use 3 significant figures, but remember that's only when you're multiplying or dividing 2 measurements. So if you're adding up molar masses, the relative atomic masses, then you go by the decimal point, not by significant figures, because you're adding, okay? And the same thing with subtracting. So the same thing applies for the Hund's rule we've just done, not the Hund's rule, sorry, the Hess's law we've just done. We're just adding. So you don't round off to 3 significant figures. But if I'm multiplying so many moles by so much mass or molar mass or whatever, I've got 2 measurements that I'm multiplying or dividing, so it must be rounded off to 3 significant figures. Yep, so April, in Hess's law, you don't need the 3 significant figures because you're not multiplying or dividing by 2 measurements. I know we're multiplying through by 2 or by 7 or by 6, but that's a factor. Okay, it's like saying I've got 1 dozen egg or I've got 2 dozen eggs. You know that 1 dozen is 12 and 2 dozen is 24 and 10 dozen is 120. Significant figures, why it's introduced is because when you measure, you bring in uncertainty, and it's to do with that. So it only affects measurements, and it's when you multiply and divide. I've done that very, very briefly. So, okay. But you go to the right decimal point. Yep, so when you're doing molar masses, you are given molar masses to 1 decimal place. So your molar mass that you calculate for a substance is to 1 decimal place. And yes, April, for Hess's law, because you're adding or subtracting there as well, you go to whatever decimal places it's given. So they may not necessarily give any decimal places. It may just be rounded off. They might just say 231, or they might say 231.1. So you just go with according to what they have given you. It should always be to the least number of decimal places. So if they gave you 231 and the other one was 1.1, you should, strictly speaking, leave out the 0.1 because the first one wasn't done to 1 decimal place. But they don't try and catch you with the significant figures in the exam, so they're highly unlikely going to give you a value to a decimal place and another one that's not to a decimal place. Because I know a lot of chemistry teachers get very confused over this issue. So when they mark in the exams, they sort of know that students can come with all sorts of ideas on significant figures. So they try and keep it quite simple. Like pH values, which is now something different again. They just They don't even go to significant figures there because people don't understand how to use log values and significant figures. Anyway, we're getting sidetracked and we have got 3 minutes left to do the rest. So what I'm just showing here is what's in the standard. So in the exam, they can ask you anything that's in the standard. So it says properties of particles, they're limited to electron configurations of atoms and ions, and it's just for the first 36. So electron configurations only are limited to the first 36, but you can do atoms or ions, and you have to do it in SPD. Don't say 2, 8, 8, 2 or something like that. That's level 2 stuff. You need to do level 3, so it's always SPD notation. And remember, of course, the 2 exceptions, copper and chromium. Remember here the 4s1 3d10. It doesn't matter if you put the 3d10 before the 4s1, it'll be accepted both ways, but you have to have 4s1 3d10, not 4s2 3d9. That'll be wrong. Okay, so you have to learn that exception, and also remember that for transition metals, the electrons get removed from the, well, for anyone actually, the electrons get removed from the outermost orbital first. So that affects your transition metals the most because it gets removed, although 4s is lower in energy, it gets removed from the 4s before it goes from the 3d. Okay, so that's just 2 little tricks, that often muddle up people, is learn those 2 exceptions of copper and chromium, and remember you take from the outermost first. So when we get to sulfur and chlorine, that's easy because that's, or the next one, yeah, sulfur and chlorine, because you now on the next energy level of 4p, but when you're in the transition metals, you've got to remove from 4s before 3d. Any questions on that? No. Okay. So basically the exceptions and the cations, you remove 4s before 3d. Oh, and another tip is you can write the abbreviated one, okay? But if you do the long version like this, it helps if you add up these numbers. So 2 plus 2 plus 6 is 10, plus 2 plus 5 is 17. Okay, I obviously haven't, that doesn't apply for copper. Okay, this is something else. Okay, you can put both in your answer, April. I'm not, if one was incorrect and the other one not, I think they just marked the first one, but I'll find out actually. Okay, but if you add up those superscript numbers, they should correspond to the number of electrons. So whatever's given the periodic table, the atomic number, and if it's an ion, you subtract or add. Okay, then you need to do the periodic trains, and you've got to compare the ionic and atomic radii. So remember what I said about pens to explain trends? P, protons, always discuss the number of protons in the nucleus. E, always discuss the electrons, the energy levels, how many energy levels, okay, which energy levels, and effective nuclear charge. So EEE, okay. N, the nuclear charge, that's the same sort of, if you're going to use the word nuclear charge and effective nuclear charge, you have to explain it is based on the number of protons, and then the shielding, which we'll get to now. D is the distance between the nucleus and the bonding electrons for electronegativity, or nucleus and valence electrons for all the others, the ionization energy, radius, and so on. And then S is the shielding. So explain these terms. Don't just say the effective nuclear charge decreases as you go down, or something like that. You've got to explain how you get the effective nuclear charge. It's the nuclear charge based on the number of protons that's been decreased because of the shielding by the inner electrons, or by the electrons in the inner energy levels. And especially for excellence, be specific. If you're talking, say, about aluminium, say it's shielding from the 1s or the first and second, well, be the first energy level. Just spell it out. Okay, and then finally, remember at level 3 include states. So if you're doing your redox report, please, I want to see states on there, okay? Anything, you include states. At level 2 you could get away with it, level 3 you can't. Okay, carrying on, I know we're going slightly over, so I'll be as quick as I can. Lewis structures and shapes, okay, up to 6 electron pairs. So you've got to learn those different shapes off by heart, okay? And the attractive forces. Now remember, you've got to do all 3 types of attractive forces. So if you do Lewis structures, first step is always show how you got the total number of valence electrons, because that'll make sure when you count your valence electrons and your dots, do they match up, or have you forgotten the lone pairs around the fluorines and the chlorines, which is a very common error. Okay, if you've got cations or anions, did you put in the square brackets and the negative charge or the positive charge? Okay, and remember, you don't want, if you're looking at shapes, you first look at the electron geometry. So you must first say, I have got 5 regions of negative charge, or 5 regions of electron density. So the electron geometry is trigonal bipyramidal. So you start with that, and then you say, but I've got this number of lone pairs and that number of bonding pairs, and you can get the shape. Okay, so it just be sort of follow a pattern. And then, as I say, follow this pattern for polarity. Always talk about electronegativity, then the dipole moments, the bond dipoles, and the molecular dipole, and then the symmetry. Okay, and then what I said with this one, hydrogen bonding, draw a diagram if you're running out of time, because it's much quicker than explaining it. And then, what I didn't say is, as a little arrow, make sure you discuss all 3 different types of intermolecular forces and the factors that affect it. So mass will affect the temporary dipole force of attraction, but not the permanent dipole force of attraction. Okay? So make sure you have all that detail. And then this is then properties, so you may have to explain boiling points. It's all to do with intermolecular forces, melting points, solubility, okay, and then entropy is needed for, if something's spontaneous or not. And then we've done the definitions, Hess's law, and of course calorimetry. Okay, sorry, I should have clicked those. So those are just things to think about. The entropy change must be positive for a reaction to be spontaneous. You do need to spell that out. You do need to know your definition so you can write those formulae like I showed you in Hess's law. Okay, and there I said all the forces must be explained, including the factors that affect the size of those intermolecular forces. Okay, and then you've got 2 types of calculations you'll have to carry out. So I think that's it. There's no bond enthalpy, so if you're going through the old expired standard, you don't have to talk about bond enthalpies anymore, in case you see a question there. And I think that was it. So any questions?